Good morning, everyone. I hope I'm audible. Okay, good. So, yeah, let me begin by thanking the organizers for giving me this opportunity to share some of my ideas with you. And I think they selected a nice topic for me to engage with different sections of the astronomy community, and namely to see what kind of challenges gravitational waves, sky localizations may pose to start this coincident electromagnetic gravitational wave observational effort. But then they added a few other things. Basically, I think the last word was etc. or something like that. So, which fortunately or unfortunately just expands the field too much for me. I mean, but I'll take that opportunity to talk about a few other things, somewhat related to the main topic. So, should we start this? Maybe. Okay. Right, so the synergy of electromagnetic astronomy and gravitational wave astronomy, I'll begin with this. Here on the one hand, for gravitational wave signals, what we are talking about are essentially transients. Yes, we have observed a couple of binary black hole mergers. We don't necessarily expect electromagnetic counterparts from these sources, but so what? I mean, I think we should nevertheless go ahead and check if the traditional models are true or not in nature, or if nature has found a clever way of circumventing what we think is realistic and get binary black holes to produce electromagnetic counterparts. So we will search. So these transient signals are obviously of the order of a second or less, given the masses of the black holes involved. But the canonical paradigm would say that neutron star mergers, like two neutron stars colliding or a neutron star falling into a black hole, those kind of binaries should produce electromagnetic counterparts. And so certainly we should look out for those objects. There, the timescales are longer. We still call them transients, but two neutron stars, each with a mass of 1.4 solar mass, when they coalesce in the LIGO band, they can keep emitting gravitational waves for of the order of 20 minutes. So from some of your talks, what I learned is, when you talk about light curves, they're usually longer, right? Longer periodicities. Here, the electromagnetic counterpart will also, maybe a transient, for example, a gamma ray burst, right? Or prompt X-ray emission. But there could also be optical afterglows, maybe even kilonovae, and I'm going to touch upon them a bit. And their timescales can be different. They can be of the order of minutes to hours to days. But one challenge we face in the gravitational wave community is that, especially if you want to catch a prompt electromagnetic emission from a compact object merger, then we better communicate our gravitational wave triggers to you very, very soon after the merger happens, or even maybe in advance of the merger. And that is because, after all, these two objects, they are emitting gravitational waves as they are slowly spiraling in. I mean, slowly initially, but pretty fast later. But that has to deal with the fact that one of you brought out yesterday, that realistically, data is non-Gaussian and also non-stationary. So there are glitches that we have to contend with. And I will show you some of these glitches which in some space masquerade as gravitational wave signals. But if you look for the right spaces, for example, time frequency maps, maybe you can discriminate between the two populations, glitches on one hand and gravitational wave signals on the other hand. Then, of course, on the hardware side with electromagnetic observatories, there are difficulties posed by how you slew to the right point in the sky and then maybe catch a fading light curve. Then there is also the fact that, especially with two or so gravitational wave detectors, we don't localize the source very well in the sky. And so how are you going to tile that large patch up, and then where are you going to point first and then next? So how are you going to rank these tiles? So those kind of interesting problems come up, and that actually amazingly opens up a vast area of maybe mathematics and theory of computer science algorithms to tap into to solve these problems. For example, for the last one, we used aspects of graph theory to find how to rank these tiles so that the total probability of capturing an electromagnetic counterpart is maximized under the constraint that this patch is going to set eventually. And the light curve may not exist for more than a night. And another thing that is important to us and has not come up yet in this meeting is that higher order statistics may play a role. I mean, of course, we are talking about non-Gaussian noise, so higher order statistics. So in that sense, it has already come up indirectly. But I show you an use of how these statistics are used to probe couplings between different oscillations or modes of a detector to create noise with power in other frequencies, which can interfere with our ability to observe some of these gravitational wave signals. By the way, such couplings can happen not just for noise sources, but also for gravitational wave sources. So keep that in mind, because I'm going to talk about that also, time permitting. So let's start with coincident electromagnetic gravitational wave observations. The physics case for this maybe is nicely captured by this plot, which I've unabashedly taken from this paper by Metzger and Berger. So when you have two neutron stars or a neutron star and black hole merge, eventually they are expected to form a black hole, but it's not necessarily going to happen instantly after the merger. Because depending on the equation of state of the neutron star and how massive they are, you can have a post-merger object that is a hypermassive neutron star that exists for some time, could be a few milliseconds to several tenths of milliseconds before it eventually collapses into a black hole. But that's a large enough window to create interesting electromagnetic counterparts. So for example, of course, so this has been proposed as a progenitor for the short duration gamma ray burst. So in this cartoon, there is this jet, which is the source of gamma rays. But to observe them, of course, this binary has to be face on because the gamma rays and also the other high energetic photons are expected to be beamed within a narrow cone, maybe 5 to 10 degrees wide. But that then reduces the chances of coincidence because we can observe gravitational waves and such high energetic photons only if the line of sight is well aligned with the axis of this jet. But as this jet loses energy by interacting with the circumbinary medium, you will have less energetic photons emitted. But then there is also the neutron star matter, which gets tidally disrupted as it falls around its companion, another neutron star or black hole. And so this shows, this red is basically neutron star matter. Some of it is falling into what in this case is a black hole companion. But then there are these large tidal tails. Some of this material will be unbound, and that material can comprise neutrons or uncompressed nuclei, heavy nuclei, which then is a nice fertile ground for our process nucleosynthesis. So these heavy nuclei are unstable to radioactive decay or fissile decay, and they can also emit electromagnetic radiation, but that has to be filtered through a lot of lanthanide elements. So what is visible to us, people have proposed, will be in the infrared region, and maybe people have already observed such photons, which we generally term as a kilonova or a macronova. So this is something that a couple of papers associated with the short duration GRB, which occurred in June of 2013. But this is like a one-off claim for a coincident observation. We have to see more of these to be absolutely sure. Maybe there was another claim in a different object, but this population better increase before we have a confidence in this kind of an association. With gravitational waves, no, we did not observe this in our detectors, and that's because advanced LIGO was still being commissioned. Remember, we started observing only in 2015. Yes, we were lucky with the binary black hole merger, but in future, we hope to observe some of these neutron star mergers as well. Of course, this object was at a redshift of 0.35, which is beyond the range of advanced LIGO for neutron star mergers, and that range ends at about 450 megaparsec. But then there are proposals for future detectors. Advanced LIGO upgraded to something like, there are different configurations experimenters are talking about, A+ or Cosmic Explorer. I'm not sure whether somebody is going to talk about them here, but I think there are people here you can speak to understand, or to learn about how those next generation detectors may help improve our chances for capturing these gravitational waves from similar binaries. But for this, we need quote-unquote theorists to be able to tell us what kind of a light curve we should expect from a kilonova-like emission. And we have to have multiple observations, multiple sampling of this light curve to be sure that it is indeed a kilonova and not something else. In this case, there's tantalizing evidence, but there are only a couple of data points, one here and there, which suggests that it may be consistent with the kilonova. So there are challenges indeed on the electromagnetic side as well. And that brings me to my maybe one and only plug on LSST. And there are some of you who obviously are already preparing for observations with it. But LSST will have a very good limiting magnitude because we would like to have limiting magnitudes of the order of maybe 26, if not even higher. Especially if you want to study the decay of this curve and be sure that it's a kilonova and not something else. Yes.
What is the salient feature? Is it some increase in the infrared after some time?
That's right, and so people have proposed these curves. So you should see a rise initially and then a fall within time scales. But problem is that these models are evolving. I'm not an expert in these models, but I know that they have. So these theories have flip-flopped a bit. Here, the light curves can exist for of the order of a day to several days. But then there are other proponents who suggest that no, these have to be actually shorter in time scales. Achromatic or chromatic, I'm not sure. I don't know if there is anybody else who would. Chromatic? Yeah, so it should be peaking in the IR. I mean, there is some bandwidth, but yeah. Yeah.
Yeah, so if you don't get that right, then you don't get the residue also.
You don't get the residual right as well. It's very sensitive to that, absolutely. Yeah. Okay. So indeed, on the electromagnetic spectrum side, there are challenges. Now, while this decompressed neutrons are emitting their own photons, momentarily, the two neutron stars are merging. Of course, this happens at a much smaller time scales, milliseconds, tens of milliseconds. But this post-merger object can also produce interesting gravitational waves, which are very different from what we observe what we expect to observe in the in-spiral phase. And that, in turn, can tell us something about the nuclear equational state of these objects. And quantum chromodynamics has not told us enough to pin down this equational state. So there are interesting complementarities there, whereby we can combine physics harnessed from heavy ion colliders in terrestrial experiments on one hand, and such observations in gravitational waves to actually more completely understand that equational state. So these oscillations, numerical relativists thankfully have been able to model. So what you see in the left-hand side plot, this is a recent work that I've done with a set of collaborators, some of them in the LIGO scientific collaboration. In blue, you see the time series of the post-merger gravitational wave strain oscillations. And in blue, you see again the numerical relativity data for the spectrum. So you see a peak in this oscillation at about between 2,000 to 2,500 hertz. Remember that for 1.4 neutron stars, they're actually going to merge at a lower frequency, very close to about a kilohertz. This post-merger oscillation frequency, in fact, tells us it is happening because of the fact that you have something like a bar mode, so that produces this quadrupolar radiation. But the frequency is related to how massive these neutron stars are, which is expected, and also what the equational state is. So as these two objects are compressing, the spatial extent is determined by, again, how stiff or soft the equation of state is. The masses determine how separated they are initially, right? How big they are, because the radius is correlated with the mass depending on the equation of state. And in addition to that, there could also be physics in the form of some viscosity effects. Yeah, the black here is our analytical modeling of the numerical relativity waveforms. And obviously, the black doesn't model things very well, except for the fact that two of these initial post-merger oscillation frequencies are modeled very well, both in terms of where this first peak occurs and this second peak occurs, and also how they damp. Okay. The reason we did not spend enough time to model the later frequencies is because, as we know, the gravitational wave detectors actually have a noise curve that worsens because of the photon short noise as you go to higher frequencies. So we won't have enough signal to noise ratio at these higher frequencies. So we neglect them. But also we wanted to keep our analytical model relatively simple and therefore more predictive and powerful. So we used just a few parameters to model for these two frequencies, which are indeed what will dump most of the signal to noise ratio in our detectors. And this was for a specific equation of state, GNH3. Don't ask me for what the acronym means. But I think it was found by Glendinning and his collaborators. And then there is H4, which is somewhat less stiff. And there also we have very good agreement, both in phase as well as in spectrum. This also was found by Glendinning with a different collaboration, I think. But then there are other equations of state, nuclear physics equation of state that we have modeled. Yeah, so these objects, I mean, in the time series that I've shown, they're still hypermassive neutron stars. But if you evolve the numerical code long enough, eventually they collapse to a black hole. Yes. Yes.
When you say analytical model, can you provide more details on
Yeah.
that?
We start in a phenomenological sense as follows. We have data from numerical relativists for various equations of state, right? We know how this frequency shifts. In fact, between the previous plot and this one, this frequency has already shifted. The decaying timescale has changed. So through multiple, and the problem, of course, is that ideally you would want some continuous, a set of tunable parameters that tell me how to dial from one equation of state to the next and so on, right? And then see how these frequencies and their time constants change as you dial this equation of state. Unfortunately, that's not possible because numerical relativity codes, they're computationally very expensive. They take months to produce one snippet of a waveform, right? So what we do is we are working with a discrete set of, limited set of waveforms, but nevertheless, we have polytropic equations of state that we can use analytically to interpolate between two numerical relativity waveforms. So that's one side of the story. The second is we know what the frequencies and time constants are from the numerical relativity waveforms, and then so we have these signal parameters. Say the f1, the f2, and the tau 1, tau 2, the time constants. We then study how these frequencies and the time constants change as you increase the stiffness or lower the stiffness.
That is done in a trial and error way, or
yes. To get started, it was done in a trial and error way, and as we learned more, we reduced our search parameter. So initially, we started with a proliferation of phenomenological parameters, and then life was hell because if you want to find the maximum in the overlap for any waveform produced by a lot of parameters, it's very difficult. But then as we learned more and more, we reduced that parameter set, and eventually it settled to something like 6 parameters.
In that regard, I was wondering if there is this whole Gaussian process modeling that can be used as a proxy and then that is run very fast. If there is a way to get around that.
Excellent. So that's exactly the type of feedback I need. From these fits, it appears that we have done a reasonably good job, but then we have not explored too many equations of state. So and it's not clear which one nature favors. So I think to be more expansive in our exploration, the model you're talking about could be useful. So maybe I should talk to you.
Are you able to interpolate between other parameters of the mass spectrum?
Okay, I'm not going to end in time, but no, I'm happy to take questions. Mass parameters? Yes. Yes.
We are able to look.
Yes. Yeah. Otherwise, it's not. I know there are initial papers that just assume certain masses, but we know actually from these studies that there are covariances, statistical covariances between different parameters, like the masses of the neutron stars and equational state parameters. And without breaking that covariance, you cannot provide realistic estimates on how accurately you can determine some equational state parameter. Yeah.
So for a given equational state, you can create a fully analytical interpolated template family over different masses of different stars.
Yeah, but in this approximate way, where I'm not gunning for some of the features, which are unimportant, honestly. Maybe for Einstein telescope, it is more useful. So that's a problem for a later day. Yeah. So, and of course, I mentioned the large error boxes that you already seen. Maybe Varun Bhalerao in his next couple of talks will talk about this more. So I'll perhaps neglect this. But yeah, I mean, just to advertise the fact that we have written a code to do the following. From gravitational wave observations, we know which regions here are more probable to harbor an the real source, right, compared to the other regions. So we can pixelize these large error bars based on the tile size of the telescope you're going to use to observe them, right? And then the question is, but these patches are going to set. So the question is, even though the probability tile here, the tile here may not have a very high probability, but it's going to set first. So should you actually observe here first before you come to a more high probability tile that's going to set later, right? So there is an optimization game, which is what I was mentioning that we use graph theory to solve. And so here we show that we observe these tiles first, although the probability here shown in red is less because these set early. This is the horizon. And then we move on to other tiles with higher probability or lower probabilities, which are going to set later. And then this is a scheduling algorithm that is already being used in different observatories around the world. Next to non-Gaussian noise, yeah, and this is realistic data from an engineering run, not very different from the engineering run data that yielded us GW150914. And we do use certain aspects of glitches to veto some of these triggers. So number of gravitational triggers shown on the vertical as a function of the signal to noise ratio on the horizontal. After veto, we still have the red bars remaining. In some cases, of course, the reds are gone, so we were successful in using those discriminators. But then in many instances, they don't go away. So we have to target these. Otherwise, we are going to provide you with these false alarms to use your telescopes and point at those, and that's not good. So we have to get better at this. In the time frequency maps, frequency in the vertical, time in the horizontal, we already know how these chirps look like. But there, again, these will show up as these chirps only for, essentially binary black hole objects. Okay, for binary neutron stars or even low mass binary black holes and that are weaker, more distant, we won't see these tracks. So that becomes a problem. But in cases where we can see these tracks, they can be distinguished from a typical glitch. This is not a typical glitch. I think this is Snoopy, and maybe somebody. It looks like Snoopy. This will be, very easy to discriminate against, right? But what we see are, and this is real, and these whistling glitches, we have names for them because, these are our, labels. And thankfully, we can model these. At least one part of this can be modeled as a chirping Sine-Gaussian, so exponentially damped with a central frequency f0 and a chirping parameter kappa, which is like, f dot. And we know the effect of these glitches, and also a non-chirping one where kappa is 0, namely this one. Such as, this glitch can be modeled as a weighted sum of different Sine-Gaussians. And we know their effect on our waveforms for neutron star coalescences. So, and this shows that effect. So you have the signal to noise ratio arising from MASH filtering data with such a glitch, like that Sine-Gaussian glitch on one end, and the expected waveforms for neutron star coalescences for different masses. Chirp mass, as shown here, is a combination of the two masses in units of solar mass, going from 1 solar mass to about 2.6. So we see that when you apply a bank of such templates on data with that one glitch, the delay between the trigger occurring and the presence of the glitch is what is plotted on the horizontal axis. And this pattern is a telltale pattern. We see this every time. And this can be distinguished from what we would see if instead of the glitch, the data actually had a signal from a neutron star in spiral with chirp mass of 1.6 solar mass. So this is sort of our light curve, and this curve is very different from that one. But this is something we are not using yet directly. This is something we found out simply because we knew such glitches actually exist in our data. By the way, the reason this kind of a delay happens can be shown through this animation. What's happening is in the green here, we have a Sine-Gaussian glitch, and we use a template, a chirping template, to do the cross correlation. So, this is basically we're sliding the template against the data with that glitch. But the trigger time is really the time between the peak frequency of the glitch and the ending frequency of the template. And for more massive templates, this ending frequency is lower. And that is because more massive objects are bigger. They are touching at a longer separation. So that is why this time delay increases as you increase the mass. Can I have 5 minutes? Okay, thanks. So we understand this, and what another group has found is the following. They were using machine learning algorithms to discriminate between glitches and signals, and our traditional statistic gives these many expected number of detections per false alarm. But if they use machine learning algorithms, they can improve. Oh, actually, I'm sorry. The red is what is being currently used, but the top curve is for outputs from a machine learning algorithm. And in hindsight, it turned out when we spoke to these authors that one of the discriminators, their algorithm output, was actually this time delay. So what this is telling us is that you may do these things in a supervised or unsupervised way, but if you do it in an unsupervised way, it is important to find out what those discriminators are and then physically interpret them. Because if this is the physical interpretation, then it actually tells us that the glitches, the Sine-Gaussian glitches that are going to hurt us most are the low frequency ones because they create the largest time delays. And that can be very confusing for our algorithms to separate. For example, if you have a glitch and you want to create a time window to block it out, the low frequency ones will demand a very long time window, several seconds. And so we lose data time. Maybe I'll end with this plot. So have whatever we learned in the gravitational wave community helped others in the wider astronomy community? And the answer is yes. And there are a couple of examples. One of them is for Kepler. Of course, I mean, so these are the eclipsing light curves you expect from transiting planets. But it turns out that you can find gaps not because they actually exist because of a transiting planet, but because of other reasons. And they are using a discriminatory test called the chi-square test that was first developed in the context of compact binary coalescences in gravitational waves. And this is the paper. If you want to learn more details about it, they use it to basically what they're doing is they're doing, you first check whether there is an overall fit for a light curve over multiple transits. And then you check if in shorter durations or smaller bins, you have consistency with the light curve that gave you the best match. And this kind of a test we first developed in gravitational waves, again, to avoid the effect of these glitches. So there is another example, and that is the Einstein at home example, where that tool was developed to observe gravitational waves from spinning neutron stars with a wobble or with a mountain, a small mountain. And that is being used to actually find real pulsars, especially in binary systems. So let me end the talk at that point, and I'll be happy to answer any questions any other questions you may have.
Comments?
What's the number of glitches that you have of different types? For machine learning, they're already being used. So is it in the thousands or millions or?
It's certainly in hundreds, if not more, per day. So we have various categories to distinguish them, and depending on the level you're talking about. But yes, I mean, quite a few to be worried about and to do something proactive about.
A good fraction of them are labeled the way you were saying about the whistles and so on?
I showed you just two related categories. There are many others. There are glitches that we don't understand completely. The so-called blip glitch is, I think, something we are still trying to wrap our heads around. Yeah. So there is a lot of scope for understanding them. Something I didn't show. Oh, actually, you're changing my talk. Yeah, I didn't talk about higher order statistics, but there are nonlinear couplings also between different subsystems that create additional transients, and we can use higher order statistics to find what they are and their causes. Eventually, it is important to understand the causes so that we can take them away or mitigate their effects. And by the way, higher order statistics can also be useful to understand the post-merger oscillations of neutron stars, and that is because there are higher frequencies. Some of them are created because of nonlinear couplings of lower frequencies, and these the mechanism ultimately is related to, for example, what the nuclear physics is of these objects.
The LIGO detectors sensitive to a certain range of masses of black holes, right?
Yeah.
But do mergers of other black hole masses contribute to the noise?
I didn't hear. So the other masses
Meaning
do what to the noise?
Which are outside the range of the LIGO detector. For instance, intermediate mass black holes or whatever. So if they merge, there'll be a contribution to the sort of noise, the ones you don't resolve. So does that, so I was just trying to understand whether the noise contribution from black hole mergers in the LIGO data are only from this mass range, or do they have contributions from the larger mass range?
The thing is that there is a point in the mass space beyond which, if you go, that signal will not show up in our detectors. That's because, and this is of the order of maybe a few thousand solar mass, right? And that is because those objects are large enough so that when they're merging, their orbital frequency is of the order of several hertz. So the gravitational frequency, which is twice that, is of the order of 10 hertz. And advanced LIGO sensitivity ends in the low frequency side at about 10 hertz. So binary, but there are always caveats. Some of these objects, although their primary frequency, the quadruple or more, it will not show up in our band. But there are other modes, and higher harmonics that can show up, but they will be at much smaller signal-to-noise ratio. But if then there is a population, and a large enough population of these objects at nearby distances, they can overlap to create a confusion noise. With increased sensitivity, we can have a confusion noise from black holes which actually have masses less than 1,000 solar mass as well. Whether that's a good thing or bad thing, I think time will tell. But in a way, yeah, we can do demographics of these objects if we have that confusion noise. Yeah.
I guess the quick answer is that we don't because the frequencies are just scaled by the mass itself. So we will have confusion noise, but only from stellar mass or intermediate mass black holes, right. Not supermassive black holes.
Okay, yeah, that is a summary of what I said. Yeah.
If not, let's thank Sukanta once again.
Thank you.